Hello, everyone. My name is Basit Kiriakou. I'm an assistant professor at the University of Groningen here in the Netherlands. You heard also the accent, Groningen. It's not Groningen. I've heard it many times. So welcome to this afternoon session about carbon capture and separation. Since there was a technical problem this morning, we skipped the coffee break. I know many of you will complain, but you will have the chance to go for a couple of minutes out and grab the coffee and come back. And also we'll try to keep the time. So I would like to ask from the speakers to be aware of their time, so we finish on time. So the first interesting presentation will come now from Technalia, from Dr. Miren Etzberia Benavides, this is easier. And the talk will be about resource recovery and CO2 capture from steel coke oven gas, and will be about hollow fiber PEVA membranes for CO2 capture from the project Kumer. Okay, your stage is yours.
Thank you for the introduction. So my name is Miren. I came from Technalia, a research institute situated in the Basque Country, in the north of Spain. And today I will talk about the Kumeri project. So on Kumeri project, the aim is to develop and demonstrate advanced and customized membranes for separation in two key industries. On one hand, we have ultrafiltration membranes. We'll be using this oil additive recovery in the oil and gas industry. And on the other hand, we have the gas separation membranes. And in the session today in the morning, Hannes has presented, so there are two types of membranes. We are developing many membranes. The ones presented by Hannes this morning, silicon carbide membranes for hydrogen recovery. And the second type of membranes, the PEVA type membranes that I will present now, and they are for CO2 capture. So why PEVA membrane and why hollow fiber membranes? PEVA membrane are known to have good CO2 permeability and CO2 nitrogen selectivity, and they are this polymer. It's available commercially, and it's mainly produced by Alchem. This polymer is a copolymer formed by a polyamide block and a polyether oxide block. And when it forms a membrane, it forms a microphase separated structure. So we have some polyamide crystalline domains and some non-crystalline polyether oxide domains. The polyamide domains is considered to be permeable to the gas, and the gas permeates through the polyether oxide non-crystalline domains. And due to its affinity to CO2, these membranes are known to be appropriate for CO2 nitrogen separation. And why hollow fiber membranes? Hollow fiber membranes have several advantages over flat sheet membranes. On one hand, the fabrication costs are 5 to 20 times lower than flat sheet membranes. The packing density is 10 times higher than flat sheet membranes because due to the small diameter, they can be packed in membrane modules with high surface to membrane volume area. And then, in the other hand, the quantity of PEVA polymer to produce 1 square meter of membrane, it's much higher if we prepare them by the spinning process than if we have a composite membrane. So it could be of interest for polymer companies producing this type of polymer. But the main problem of the actual commercial PEVA membranes is that the solubility is limited and they cannot be processed as hollow fiber membrane by the spinning process. So they only can be processed by deep coating. So our idea is to modify the chemical structure of this PEVA polymer to be able to dissolve in the solvents used in the spinning process. So our work in PEVA hollow fiber membranes started with the Biocommon project and then continued with the Kumeri project. In the biochemistry project, we produce some PEVA polymer where the PEA block was bio-based, and then in the Kumeri project, we produced the PEVA members where both the polyamide and the bio block were bio-based. And the aim in both projects was to modify the chemical structure of the PEVA to be able to be processed as hollow fiber membrane by the non-solvent induced phase separation. And here you can see the ideal structure of a hollow fiber for gas separation. The ideal hollow fiber for gas separation is composed of a highly porous support and a very dense thin separating layer. This layer should be as thin as possible. So as I mentioned before, we started working on PEVA hollow fiber membrane with biochemistry project, where dimer fatty acid derived polyamides were used for the synthesis of the PEVA polymers. So several lab scale polymers were used. In that case, the polyethylene oxide block was kept constant, and different polyamides were used for the membrane synthesis. Of course, once the polymer was synthesized, we determined the CO2 gas separation properties, but rather than that, we also check if the polymer we synthesized, if it was stable in water, if it was soluble in NMP, and also if it was able to form a cell-supported membranes. So the polymer that fulfilled all these requirements was the one highlighted here, and this was the polymer we scaled up, and then we use it for hollow fiber preparation. So the hollow fibers were prepared by the non-solvent induced phase separation by the spinning process. In this process, a polymeric solution is co-extruded together with the bore fluid through the spinner. The polymer we first selected for spinning was a polymer where the polyether oxide ratio was of 70 to 30, and this was the separation properties of the intrinsic separation properties of the polymer. So we spin the fibers. Here you can see the optical microscope picture of the wet fibers, but what we observed was that when we dry the fiber, the porous superstructure of the polymer we observed in the wet fiber was completely collapsed, and a completely dense hollow fiber membranes was obtained. So what we tried next was to spin some fibers, but in a dual layer configuration. So what we did was to co-extrude two different polymers. The polyamide and polyethylene oxide block of these polymers were the same, but the ratio of both were different. So we increased the polyamide content of one of these polymers in order to avoid the pore collapsing during drying. So we co-extrude these two polymers, and we obtain a dual layer hollow fiber membranes where with a porous superstructure, you can see here, and a thin selective layer in the inner side of the membranes. Even though the selectivity was not the maximum we can achieve with this polymer, but was not too bad. And what we also observed was the CO2 permeance was too low, and this was mainly due to the thickness of the selective layer, that it was a bit thick, it was about 10 micrometers. And then in some region of the superstructure, the polymer was also densified. And this is why the permeance was too low. But we see that there was still some room for improvement with this type of polymers. And during the Biocommon project, this valley flow fiber were scaled up, and so different bundles were prepared with this polymer. And we observed that the gas permeation results were quite similar and continuous during the spinning process. So, as I mentioned, the Kumeri was a continuation of a Biocommon project. So we took the polymer developed in Biocommon as a starting point for the polymer at Kumeri project. So in the Kumeri project, the idea was to introduce certain fraction of shorted chains, diacid and diamides, in the block polymer in order to increase the melting point of the polymer. Also to replace the polyethylene oxide by a bio-based derived from starch to make the polymer fully bio-based. Then the ratio of polyamide and polyether was also modified in order to optimize the gas separation performance of the polymer. And then we also work in the introduction of reversible cross-linkable units in order to improve the membrane stability and allow the chemical recyclability of the polymer. And then on the other hand, we also investigate the use of less toxic solvents for the membrane production. So during Kumeri project, different polymers were synthesized at lab scale. More than 30 polymers were synthesized, and the polyamide monomer composition and the polyethylene block composition was varied. From these all polymers, in the first, the one with reference HS10 was selected for scaling up. And this scale up was performed by before plastic. And then some other polymers were also scaled up. In total, 3 polymers were scaled up to a 10 kilogram scale. And then during the Kumeri project, polymer was processed into hollow fiber membranes. So 2 different strategies were followed as at Kumeri project. So first, we tried to spin a single layer hollow fiber membrane with the selected polymer at the first time, and then we also tried the dual layer spinning. And it's worth mentioning that during the Biocommon project, NMPS was used as solvent for this phase inversion process. And in the Kumeri project, we found an alternative solvent to replace this NMP. And the solvent was the N-butyl pyridine. So first, we tried to prepare single layer hollow fiber with this polymer, the HS10, and then with the HS36. But we observed that the polymer with the HS10 polymer, it was not spinnable. The mechanical stability of the polymer was not enough, so we were not able to produce a continuous fiber. And then with the polymer, with this other polymer, we managed to obtain a continuous fiber. But what we observed was that the polymer superstructure was collapsing when the polymer was drying. So it was not possible to measure the gas separation performance of this fiber because it was too. So the permeance was too low. So what we did then, it was to select a polymer with a higher polyamide content. So this polymer was spin as a single layer hollow fiber membrane. And what you can see here is that we managed to obtain a highly porous fiber. And when we tested it for gas separation performance, we observed that there was not selectivity because the polymer was completely porous, but the CO2 permeance was quite high. So what we are working now is so this polymer will be the base for the production of a dual layer hollow fiber membranes, where we will use this highly porous polymer as the support layer, and then we will co-extrude this polymer with another selective polymer, which will go inside the fiber. So our idea is to get a dual layer hollow fiber as the one we get at the Biocommunity project, and this is what we are working right now. So as summary of my presentation, I can say that fully bio-based material processable with bioabsorbing and with high CO2 nitrogen selectivity of 30 was obtained in the Mori project. So we successfully scale up the polymer synthesis up to a 1 kilogram scale without losing the gas separation performance of the lab scale polymer. However, as I mentioned, we observed some densification of the fiber during drying for the single layer hollow fiber membrane, and this is why we are working on dual layer hollow fiber spinning. And it's worth to mention also that an alternative solvent was found to replace the toxic N-methylpyrrolidone. And that's everything from my part. Thank you very much. If there is no question, I will be happy to answer. Thanks.
Thank you for the nice talk. Questions from the audience?
Adesso considerare meeting after 10 years, I think. Okay, just a couple of questions on the type of fibers you're spinning. Can you give us some information on the temperature that you're using, if you're checking the humidity, and even in the solution that you're using, like PPAX with an MP, if you have any additive to increase the force, or I don't know, on solvent there to help in the mixing?
So we, in some cases, we study the addition of polyethylene glycol, polyvinyl pyrrole into the solution, and we are also using some lithium chloride in order to avoid the gel formation of the solution. And then during the air gap, there is a chimney to keep dry, because if you have some humidity in the air, you can promote the phase inversion in the surface of the membranes, so then you can form some non-desired forms of defects.
Thanks.
Questions? If not, I have a question about if you have considered any kind of impurities and how this could affect your performance, permeability, or stability of your membranes. Impurities in terms of the CO2 feedstock that you're using. So from where your CO2 will originate? So the CO2 will come 100% today. So the retenting out of the process will be, so after the oxycombustion, you have this CO2 nitrogen mixture.
And I think it could have some impurities. But
Do you think this would affect the performance of or the chemical stability of your membrane?
it could affect, but for sure, we will need some cleaning system before our membrane system. Because for polymeric membranes, the gas should be as clean as possible. Yeah.
Thank you very much. Let's thank the speaker again. Now we're going to proceed to the second presentation that will be given by Professor Ferdinando Costantino from the University of Perugia. And the title of the presentation is Aluminum and Zirconium Fumarate Analog MOFs based on C4 linkers with different functionalities. And we're going to talk about the structural insights and CO2 absorption properties. This is part of the European project done for CO2. And yeah, thank you very much. And
thank you. Good afternoon to everybody. And I'm Ferdinando Costantino from University of Perugia in Italy. And I work I'm employed in the DAM for CO2 project. And today I'm going to talk to you about some application of inorganic frameworks in carbon dioxide absorption properties, especially those based on aluminum and zirconium, using linkers similar to fumaric acid that has some advantages. We are employed, our unit, and working in the University of Perugia, but our unit make part of a consortium of universities. So you see we have 3 Italian universities in the project, 2 in Pisa and Perugia. And our task is devoted to the preparation of materials. In my case, we want to prepare and to scale up and to modify some synthesis of some benchmark MOFs already used and already tested for carbon dioxide applications, in order to substitute some and to fix some issues, like for instance the use of green solvents, the possibility to use to make solvent-free synthesis or using mechanochemistry, for instance, in order to make a scalable synthesis, and also to act in order to control the particle size and morphologies, because the main objective of this work is to prepare solid solvents to be mixed in mixed membranes for the part of carbon dioxide absorption. MOFs, especially those based on aluminum and zirconium, get the interest because they have exceptional chemical and thermal stability. They have highly insoluble. They can be used in various environmental conditions. They can be prepared by using green, sometimes green and sustainable technologies. And they have they are promising for application in gas separations. And the idea is the simplicity. You know that this year MOFs chemistry was awarded with the Nobel Prize, and the main application which allow to be awarded for this with this prize are related to simple. The simplicity was the main issues, because for instance, small changes in the linker engine, you can improve the quality of your material, you can improve the properties in many fields. And for that, we want to explore ligands very simple, those based on C4 that can form literature synthesis, and you can change some atoms in your chain, in order to check the relationship between structure and properties. The selection criteria to go on with the study of these materials are based on overall carbon dioxide load and capacity that should reach at least 3 millimole per gram at ambient room temperature, high selectivity at least measured by YAST method, to be factor tested in vector analysis. And also we are also focused on in the heat of absorption. Best heat of absorption in MOFs should be in the 30 to 40 kilojoule per mole range, because of easiness in regeneration. and also the scalability and the particle size tunability. The morphs, the ligands we are interested in are similar to fumaric acid, but they are abundant, cheap, and they can be available. They can be obtained from biomass valorization. There are a lot of advantages to use, for instance, mesaconic acid, aspartic acid, tartaric acid, taconic acid, and so on, that are based on the same C4 trans decarboxylic ligands. There are a lot of chemistry in aluminum morph. And many of these morphs have been developed in the commercial scale, at industrial commercial scale. For instance, the 120 started to be employed in real flue gas applications. There is the aluminum fumarate morph that was the most famous one that was commercialized by Basque Chemical Company, which space-time yield of 3,600 kilogram per meter per day of STW, and it can be obtained in a very mild condition. And it has this carbon dioxide uptake properties, and this also methane uptake properties. We started to modify this linker by using aspartic acid, and we got first example of this morph similar to the previous one that can be obtained only in green condition. That's green condition meaning that it's not possible to obtain just in water, or cannot be obtained in DMF or other solvents, but it can be obtained in gamma lactone, that is considered a green solvent with a boiling point that makes some concern for the purification. But as you can see, it has a diffraction pattern, not so much crystalline, but very similar to that one of fumaric acid. As a matter of fact, we were able to describe the structure with the FT calculations. This is the FT optimized structure. As you can see, the amino groups are pointing towards the channels. We also compared the FT calculated spectra with the experimental one. As you can see, underlying some similarities, but we also made some insight characterization by using solid state and NMR. For instance, by coupling the heterocorrelated spectra of marked nitrogen and protons at long contact time. As we also collected both direct acquisition on the nitrogen, the 50 nitrogen for long contact time, and also the proton. The main issues are that the protons, the nitrogen is almost protonated. That means that this morph contains also counter anion into the structure. This is the main problem. That's that limit the overall interaction of carbon dioxide with nitrogen. But also the morph is quite pure because the aspartic acid can be well evidenced. This is the textural properties. This can be activated at high temperature and very high temperature at 200 degrees overnight. As you can see, the appearance of OH group, the free OH group, meaning that the morph is fully activated. The BT analysis is around 600 square meters per gram with a very narrow per-cell distribution. And carbon dioxide properties, this morph is able to absorb up to 3 millimole per gram at 0 degrees Celsius, with a good selectivity. The gas selectivity measured over nitrogen is around 80 at the full coverage. But this morph is also some stability issues because at 200 degrees, the morph decomposes in fumaric acid and with the loss of ammonia. Meaning that after several cycles, you can obtain a mixed morph of fumarate aspartic acid because it starts to lose ammonia. That's the main stability issue. From the FT analysis, the best structure, the best simulated structure, place the carbon dioxide in these small channels, interacting with the protons, coming both from the aluminum chain and the aspartic acid group. Moving toward the zirconium morphs, there are a lot of morphs based on zirconium. The most famous one is the IWSCT based on terephthalic acid and all its derivative. Then you get the trimesic acid, the morph 808. There are other morphs based on porphyritic based linkers. But those one based on C4 carboxylic acid have been also reported. And for those one, there are some very, very important results. One is for instance, there's a paper published 3 years ago, where if you mix fumaric acid and mesaconic acid in a more or less 1:3 ratio, you are able to modulate the post sides and to block, for instance, methane from a nitrogen-methane mixture, meaning that this morph is able to separate nitrogen from methane. It's a very complicated separation because there are all polar molecules. And also you can also tune the carbon dioxide structure by mixing, for instance, aspartic acid and fumaric acid. So there is a good opportunity for to me to work with the mixed linker MOFs. And this carbon dioxide absorption of MOF 821, as you can see, is get up to 4 millimolar grams. But if you change fumaric acid with the mesaconic acid, you get a lower overall uptake up to 2.5 millimolar gram, but with a better rate of absorption, meaning that this substitution can also improve the physics absorption mechanism with a better affinity toward carbon dioxide. This is the comparison between the two curves. And the two curves, as you can see, the MOF 801 has these isotherms, while the MIP 203 has this other isotherm, which a steeper increase of carbon dioxide at low pressure, meaning that a stronger interaction exists. If we look at what happens at the carbon dioxide inside the pores, you can use also dynamic solid state NMR, and you can see a heterocorrelation between the protons of the linkers, of the fumaric and the fulminated linkers, making them off, and the carbon dioxide. Let's probably stabilize the carbon dioxide inside the pore, which has an isotropic behavior restricted into the MOF with a rotation angle around 47 degrees, measured around the channel size. Last example is the zirconium mesaconyl that was also being reported in literature, but also in this case we changed the synthetic condition, and we used the gamma valeriolactone instead of the MF, so a green solvent, and we got very nice crystals with a very narrow distribution size around 200 nanometers, so that make this morph possibly useful for mixed membrane mapping. And also in this case, this synthesis led to good isotherms with a neat improvement of selectivity of nitrogen carbon dioxide selectivity around 80. That is at least the just selectivity to be tested in future analysis. So just to conclude, the outlook, the perspective of this work is to explore mixed linker MOFs to tune carbon dioxide capacity selectivity, so to mix the linkers in the right way to enhance these properties, and also to work in the other task that means make this material useful for mixed matrix membrane for the overall scope of the project, to the part related to the carbon capture conditions. And also clearly the scaling up is also another task important to be taken in consideration. So thank you very much for your attention.
Thank you very much for the nice and clear presentation. Questions?
Very nice presentation. What about is water stability? These MOFs?
The MOFs are released for all water stable at first approximation. That's it's always. But water stability is an issue of MOFs that, in my opinion, is not been tested for a long time, for several. So water stability is always a problem for MOFs.
Questions? Have time?
Laura Zelona from University of Vigo. I wanted to ask you about, did you check how is functionalization in your C4 linkers, how does it affect the thermal stability that you said was an issue? Yes.
Yeah. It affects the thermal stability because there is a solid state reaction in terms of where static acid is decomposing at activation level. So we need to slow down, to get down the activation temperature, because to increase much. If we are able to decrease the activation energy, we are pretty sure that it's not going to decompose. The problem, to me, the problem is that the static acid is photolytic and it forms ammonia that is a very good escaping group. We need to avoid the photolysis.
Other questions? I have one small question that I was actually more curious. If you set a number in the beginning about you want to achieve CO2 uptake of 3.3 millimoles per gram, at the end you achieved with the MOF 801 4.3, so you are above the target. How this number originate? So how you set this target of 3.3? How this was calculated? Based on what?
You mean the number, the more for
Yeah,
the one we measured on
the KPI that you have.
No, I think that's normally this number is but well, if you get more carbon dioxide, is better. But the 3 millimole per gram is accepted as target point for application area.
For commercialization.
For commercialization, yes.
Okay. Thanks a lot. So let's thank the speaker again.
Thank you.
And can proceed. The next talk would be, I suppose, online. Yeah. I think it's okay. Share the screen. Yes. Laura, can you hear us? Laura, can you hear us?
Yes, I can hear you. I think now you can hear me as well.
Okay. Yeah. Please share your screen if possible.
So I need to have permission for sharing. It's inactivated in the Teams. Could you please check?
You try now to share?
I think maybe now.
Yes. I think it works.
Okay, I'm trying. I don't know if you can. Can you see my screen in full
Yes,
presentation? Okay.
Yeah, it is good. So, so the next talk will be given by Dr. Laura Talens from Universitat Autònoma de Barcelona. And the talk will be about eco-design parameters for more sustainable technologies, and it's part of the project CONFET. So, Laura, we can hear you, so please start.
Okay, well, so thank you very much for this opportunity to share the advances that we are making on the Confetti project regarding the assessment of the sustainability of these new technologies and the inclusion of eco-design parameters. I'm not sure how many of you are familiar with this project, but in this project, what we are trying to do can try to see the pointer works. We're trying to optimize, yeah, some of the waste flows that are generated in agricultural systems. Specifically, we're trying to valorize the excess of nitrates that can be produced from lixiviates in agricultural yields. And with these excess nitrates, we are using a photochemical reactor to generate ammonia. And then on the other hand, we are also designing an electrochemical reactor that is able to cater emissions of nitrogen and CO2. This electrochemical reactor is actually powered by a soil fuel cell, yeah, and the objective again is to provide, in this case, is a fertilizer, a urea fertilizer for this agricultural field. As part of the core of our work we are doing here at UAB, the point is that we know that this project is aimed to be sustainable as we are trying to valorize some of these waste flows that we are using as input for our technology. Still, to make sure that these technologies are sustainable, it is important to assess them environmentally, yeah? And as part of that, we are also aiming to include eco-design parameters, yeah, that are indeed reinforcing the idea of having technologies that are more sustainable. In here on this slide, you could see a picture of the different parts of the technology that we are using that I commented already before. And some of the questions we're making around these technologies are what are the critical function of them, if there's any key or critical component between these technologies, and how we can define also fit-to-purpose metrics for these technologies. Yeah. In order to advance in this discussion, what we have done is to propose a methodology, yeah, a methodology where we discuss eco-design criteria, yeah, that contains 3 main steps. This methodology is basically a participatory approach, where we are asking the academics that we have within the consortia that are experts on materials and technologies and experts on eco-design and life cycle assessment are guiding the discussion on how to define these criteria and how we can apply them to the confetti technologies. So the first step is especially this is important to make this decision at the early stage, so at the prototype development, so with the objective of anticipating possible problems that we may have at the end of life. So if we can already anticipate what are the key components that may have a greater environmental impact on our products, we can try to redesign these technologies to avoid these problems. So this was one objective. And then, of course, for us, it's very important to gain a more clear understanding on the components that are part of the technology and what are the limitations that these technologies could have in terms of functioning, yeah? Because we're also assessing technologies that are functional. It's not only that we want to make an environmental assessment of a technology, but we have to ensure as well that this technology function well, yeah? So once we have made this definition and description of each of the technologies that are part of confetti, we did a review of the different variables, yeah, that we could use for the assessment. So one set of variables were coming from the qualitative assessment of life cycle criteria using a methodology called EdTool. We also use the circularity scoring system proposed in another publication that is based on material efficiency standards that have been published by the CNCNLEC in Europe. And of course, we also use this new piece of regulation, the European Eco-Design and Sustainable Product Regulation, as a source of criteria. Indeed, in this next slide, we are trying to illustrate all the indicators and parameters that the European Commission is including in this new regulation, and that at some point should be taken on board by companies providing products in Europe. These products are aimed to be commercialized within Europe. Yeah. So in this diagram, I just want to mention that in here, the central part of the diagram is containing the different life cycle stages of the production of these technologies. And in here, you see with different colors, some of the indicators that could be quantified and assessed. We have also another set of indicators that is in an upper, that are on our upper level, like the use of substance of concern, the use or consumption of energy, water, and other resources, and also the use of content of sustainable renewable materials. So this is information indeed that sometimes we are collecting as part of the life cycle assessment, but here is aimed to complement some of these eco-design parameters defined in other stages. And then other indicators as the environmental footprint of the product, carbon footprint, and material footprint. So with all of that, what we did was actually, from all these 36 eco-design parameters I was illustrating in the previous slide, we did a classification. So we classified 11 of them that are planned as part of the life cycle assessment. There are also other 5 indicators that are part of the results of the life cycle assessment. But then we had a group of 20 parameters that are more complex that need to be assessed separately. So in order to understand from which of these 20 indicators were relevant for each of the confetti technologies, and to make a selection, because of course we cannot cope with the calculation of these 20 plus these others indicators we're commenting from LCA. That will be maybe too much information. We did a prioritization of these parameters. Basically, we did a Delphi-style analysis where we shared initially some questionnaires to the partners, and we asked them to complete these questionnaires and collect this information. And also we did a discussion in a workshop, online workshop, in order to reach consensus on them. So what was the content of this workshop? Basically, in this workshop, between these 20 parameters, what we were trying to understand was if these parameters were easy to understand, if these parameters will do any affection on the functionality of each of the technologies, like the electrochemical reactor, but also on the biobattery and the photochemical reactor. If they think that they were easy to measure from their perspective, and then which of the 10 most important parameters will be the most important to include, as a way of having a ranking to identify some of these ones. So after doing this Delphi discussion with each of the technology as part of the competitive, we came up with a second part of the results. And basically what we have defined now, and that's what we are aiming to develop in the next months, is on the one hand, of course, we have the indicators from the life cycle assessment that we are developing, but in addition to those, we are going to be including, in the case of the electrochemical reactor, 9 other priority parameters that are coming from the eco-design regulation. And this includes the reduction of material consumption, the cycles of use of the reactor, but also of the parts, the technical life of the reactor and also some of the parts, the use of standard components, the number of destructive steps to disassemble this reactor, and the recyclability of the reactor. So we're going to be making this assessment with all these 25 parameters. In the case of the biobattery, we have the 16 LCA-related indicators, as we commented before. And then in the Delphi-style discussion, we came up with new 5 priority parameters that are also, as mentioned before, disclosed in the new regulation. And these 5 priority parameters refer to the cycles of use of the biobattery and their parts, the technical life of the biobattery and their parts, and the use of standard components. And in the case of the photochemical reactors, we included 3 new priority parameters. The first one was the reduction of material composition, and then the technical life of the photochemical reactor, and of the most important parts that are included. So now we have, for each of these technology, let's say a list of between 20, 25 parameters that will be assessed. In the next slide, I just wanted to illustrate an example of what when we mean a parameter, what are we really trying to measure? Yeah. So, for example, one of the parameters that was selected was the cycle of use, and this is very much linked with the durability of the technology. And the cycles of use can be accounted for the complete product, in this case, one of the reactors of the biobattery, of some of the critical parts. No, this could be, for example, in the biobattery, the electronics, no, that are used to manage the energy generated by a biobattery. Yeah. So for these two parameters, what we are aiming to do when we account for cycle is we are going to be accounting for the number of cycles that the product or the product part can fulfill before needing replacement. Yeah. So in this table, what we wanted to show is that behind each of the parameters that we have selected, we have disclosed a very specific accounting methodology, and that's what we are gonna be doing in the next months as part of the project. So overall, what we can say is that this new regulation on eco-design and sustainable products is actually providing a very detailed list of criteria and parameters to advance towards a more sustainable design of technologies and products. But it is true that this list is very extensive. Yeah, we are talking about these 36 parameters, and these parameters are not always well understood by experts. Therefore, at the time of trying to selecting them and trying to identify which are convenient to improve the eco-design of these technologies, there's a need to have a more comprehensive analysis on them, and specifically on how applicable they are on these technologies. Yeah. So then we believe that having these discussions where we have experts on technology and eco-design and environmental experts on these parameters is essential. Yeah. And now we're going to be investigating how these additional eco-design parameters combined with life cycle assessment results could indeed lead to a design of a more sustainable technology. Yeah. In here, we are also accounting for the content of critical raw materials. I didn't talk much about it in the presentation, but it is also an important aspect that we are aiming to account. Yeah. So, having said that, I just want to mention that if you want to know more about all the parameters that we have been revised and the accounting methodologies we have disclosed, you can check this paper that is available in open access online. And I think that's all from my side. So thank you very much for your attention.
Thank you for the clear presentation. We'll have time for questions from the audience. I was wondering, so at some point you show something that attracted my interest about the destructive steps on electrochemical reactors. Can you, because you just mentioned it a little bit more general, I understand, can you give an example of an electrochemical reactor and the destructive steps that you have considered?
Yes, well, we have not yet reached the point where we are making actually to account for the number of destructive steps, what we will need is actually to disassemble this reactor. Yeah. So one important part that we are aiming to is to have a more descriptive information about all the parts that are contained in the reactor. What are the linkage between them? Because in some cases there might be some parts, like in this case the ionogels or ionic liquids, which are placed on a specific parts of the reactor. So we need to understand exactly where is the location and how accessible is this location, and then understanding if the fixtures that are used, for example, in this case of the ionic liquid or ionogel, are reversible. Yeah. So this means that we can maybe easily replace this part. Yeah. Or either if we need to make any destructive actions, no, like taking out adhesives or some other components, yeah, that makes probably some of these parts not longer usable, yeah. So, so in the electrochemical reactor, we have as key parts, we have the ionic liquids or ionogels, but we have also the cathode and anode. So understanding how the assembly of all the reactor is made and what are the relation between these parts, it's very important to understand how repairable, how reusable some of these parts are. So we are hoping that this investigation that we will make will also help understand, you know, the sustainability of the technology, not only from a life cycle perspective in terms of CO2 equivalent emissions, but also in terms of the lifespan and how we can make this technology have a longer technical life. Yeah.
Great, thanks for the clarification. Any other questions? If not, let's thank the speaker again, and thank you, Laura. Then we come to sleep.
Thank you very much.
So the next presentation is also online, or it's live. Will be given by Dr. Stefano Giancola from Orchestra Scientific, and will be about unlocking affordable and sustainable CO2 capture and purification, and it's part of the work that going on the project of Superba. So thanks for joining, and the stage is yours.
So thank you for the introduction, and it's a pleasure to be here today with all of you to present you a technology that can really have an important impact on the CO2 capture field. So I would like to start with an example. So an important issue we have nowadays is to reduce the CO2 concentration into the atmosphere. I would like also to mention that most of the CO2 goes to the atmosphere because of flue gas industrial emissions. However, CO2 is not just a contaminant, so it's not just a greenhouse gas, but is also a valuable resource because it can be used for many applications. So I guess that you agree with me, especially people that are attending this workshop. Now, the question is what we can do to, let's say, solve this problem. So basically in a, let's say, desirable carbon renewable cycle or process, basically the idea will be to take this CO2 from its emission sources and convert, reuse, or eventually store it. However, to do that is important to capture and concentrate the CO2 that comes out from these emission sources, because it's not possible directly to convert the CO2 to valuable resources, or most of the technology are problem doing this. So CO2 capture is an important step of this value chain. However, this is a really challenging step. Why? First of all, because of the price. So to capture CO2 is actually expensive. So to give you an idea, nowadays the CO2 capture price goes in between 60 and 90 euro per ton, depending on the concentration of the CO2. So basically, lower is the concentration in the flue gas, higher is the price. So basically, to give you an idea, the emission allowance here in Europe are around 75 euro per ton. So basically, companies prefer to emit than capture. And if you take into account that this is just the first step of the value chain, you can understand how to reduce this price is really important. Then another important issue is the purity, because to convert, reuse, even to store the CO2, we need high pure CO2. And to increase the purity to more than 99%, for example, is even increasing more the price, around 30 euro per ton. Most of the technology, they are not versatile, so they are efficient just in a limited range of operating conditions, while industrial sources are really heterogeneous in terms of CO2 concentration, impurities, temperature, pressure, and so on. A benchmark such as a mine, they have environmental concerns because we have toxic emissions. Finally, as I was mentioning, the impurities, because flue gases are the really dirty gases. So, in orchestra, the technology I'm working for, basically what we are doing is to capture CO2 from flue gas sources and convert it into highly pure CO2 in one single step at room temperature and pressure, so reducing to more than 50% the price of the competitors. Actually, we are not just doing that, and as you will see in the presentation. So, at the core of our technology, there is a MOF. This year is the year of MOF, is the year of the MOF, especially. This MOF has been invented by Professor Rosera Mongala Mascaros, that is here in the audience, that is professor of ICREA professor working at the ISIC. It's a non-critical raw material, can be synthesized at the industrial scale, is a high-performing CO2 selective physical solvent, but is very versatile because it can be used to separate chiral molecules, chiral. So these open up a lot of interesting, let's say, perspective for pharma separation, volatile organic molecules like hydrocarbons. So you can see how extremely versatile is this model. It's patented all around the world, and so Orchestra was born as a spin-off of the SIC to bring this technology in industrial scale, and we have the right of the patent. So let's start with some properties. This MOF is a high-performance CO2 selective solvent. Why? First of all, because it says good absorption capacity. You can see that at room temperature, and yes, around 4 millimole per gram of absorption capacity at ambient pressure, and this can increase up to 6.5. It's in the pressure up to 10 bars. You can see that the absorption capacity of CO2 is much higher than the one of the nitrogen. So these bring to a very high selectivity and condition more than 200 or even 250 for a typical flue gas mixture with 10% of CO2. Another important characteristic is the isosteric heat of absorption that ranging between 40 and 20 kilojoule per mole. So this means that it's a physical solvent, and this is important to allow easy regeneration. Also, it's important to see how most all of the CO2 can be raised with low absorption energy, because we have low absorption energy at high CO2 loading. And you can see a difference with the isosteric heat of absorption of nitrogen, because the one of CO2 is much higher. You can see also as well, these one are experimental and simulation data. Simulation data was performed by the Professor Sofia Calero team and Susan, that she is here, and tomorrow she will do a presentation dedicated to the simulation part. So if you are interested, tomorrow you can go to listen to her. So the technology we are using is a vacuum with gas absorption technology, basically. So in an hypothetical system, we have two columns working in tandem. So if we take into account one single column, what you have is a flue gas entering in the column. So the CO2 is selectively retained in the column. And when it's saturated, basically we apply vacuum at room temperature and we recover highly pure CO2, you will see later. So another important challenge we have to go to real industrial absorption technologies to shape the MOF into pellet form, because we cannot work with power. So basically what we did is to produce target pellets of round shape. Around our target is around 3 millimeters and mechanically strong because you can see full crush strength test compared to zeolite. So you can see that we have same property. So they are mechanically strength. So here, let's go in more, let's say, more in deep to the property of the material. This one are fixed bed measurements. So we actually measure real separation performance in flow condition. You can see that we can separate, we can capture CO2 from real flue gas mixture with 10% in this case of CO2. The absorption capacity match the one of the isotherms, and you can see the extremely high selectivity because nitrogen is going so fast from the column that it's even difficult to measure the absorption capacity. Also, you can see that we can recover almost all the capacity of the MOF, more than 95%, just applying vacuum and room temperature, very in a fast way. So let's go to see if we go to measure the CO2 that we recover, we can see that we can recover more than 85% at more than 99.99% room temperature and just vacuum. Very impressive result. So let's say shift the focus from the CO2 to the nitrogen. What happens to the nitrogen? Well, actually we have an extremely as well pure flow going out from the column with less than 0.5% of CO2, and we have basically nitrogen and as well NOx component going out same time that can be valorized. You can see here the breakthrough curves of the NO and NO2, so you can see that they are weakly absorbed in the material. Stability to contaminants. NOx, so accelerated test, 1000 ppm, and as well water. You can see that the material recovered almost the performance after the cycle. So this is actually another outstanding result. So I would like to mention that the orchestra and this technology, the orchestra is partner of the SuperVal project. The overall objective of the SuperVal project is to basically separate flue gas component, and that's where orchestra is playing the role, and convert basically the components into formate through a photo driven electrolyzer and to ammonia, nitrogen component to ammonia through a photo assisted chemical process. And tomorrow, Professor Seramon will give you, if you want, an overview of the project. I would like also to mention that we are in the portfolio because the CO2 and nitrogen portfolio of the European Innovation Council, that's the Pathfinder call. We are working. So I would like to end this presentation mentioning that orchestra is not just doing the flow gas capture, but we are doing as well biogas upgrading, capturing and purifying CO2 from fermentation process. So, for example, small agro-food companies, and as well hydrogen purification. We are doing as well this in the SuperVal project. To conclude, the MOF is an high versatile MOF based on non-critical raw material and can be synthesized at the industrial scale. It's a high-performing CO2 selective CC sorbent to be used for carbon capture application as an absorbent. We can shape it into pellets of good mechanical strength. We can reduce the energy because we can work at basically room conditions. We can recover high gas purity for downstream conversion, and it's stable to contaminants. So thank you I would like to end thanking the orchestra team, thanking the collaborator, the founding, so the European Innovation Council, the SEDET in Spain, the portfolio, and the Sofia team here, Rob, and you for the attention.
Thank you for the very nice presentation. Questions from the audience?
Stefano for the next presentation, and just wondering, the activities can be due to the presence of unsaturated metal sites.
The selectivity.
Yeah.
Yes.
And rise from this feature.
Actually,
They have seen that Tracia contains the water molecule related to.
yeah, this both actually has open metal side. But as you can see, when you see the 95% of working capacity, basically the selectivity, the part of the open metal side is not, let's say, taking role in real application. So basically the selectivity is not just that, is the let's say affinity.
So it's not compatible with water.
If you see the isosteric heat of absorption, this part is the part of the, let's say, stronger CO2 attached to the MOF. But when you are in real the absorption cycle, this is not taking on. So it's not, let's say, the main reason of the selectivity. We have good selectivity in even if we don't take into account this, let's say, part that is anyway.
Other questions? We have time.
For your presentation. So I saw that for the adsorbent you are using it for flue gas applications. So I just wanted to know whether you have applied it in low CO2 concentration situations, like direct air capture, where we have low CO2 concentration, but maybe when there's high humidity, we have a lot of moisture. And also another question, how does the adsorbent react when you have high humidity? Is it more selective to, or you still have the selectivity?
Okay, so concerning the first question, we are interested in flue gas. So we can work with very low CO2 concentration, flue gas with very low CO2 concentration, 5, 6. Concerning direct air capture, preliminary data show that we can apply this material for direct air capture, but as a company, let's say it's not our market interest. So it's a question of business, but we have no, let's say, if you let's talk about TRL. We have, let's say, we are in a lower TRL for direct air capture. So, but in principle, we could use, even if it's not our interest from now, because we have to as well focus the resources on this, say, opportunity. Concerning the second question about humidity, of course, the water compete with the CO2. The cubes you saw was 72, if I remember, percent of relative humidity. That is quite high. It's true that if we increase a lot the water, what we see is a competition between CO2 and water. So basically, we should work, the material is stable, but maybe we should work at a higher generation temperature than temperature. So we prefer to, let's say, reduce the humidity, even if the material is stable.
Another question? Yes, about if you have considered in case of SOX, if they are present in the feedstock, do you have any issues with it?
Okay, yeah.
How it is?
No, we know that we have tested with fluorescence. It's stable as well. In this case, let's say scientifically, the target of the project were specifically the NOx. So what I showed was the NOx, but we have data, let's say, proving that is the material is stable as well to stable. I mean, these kind of gases the material is quite stable. So that's the feedback we have. But in terms of breakthrough curves and so on, that was not the target of the project. It's very difficult to test all the impurity but we have, let's say, good feedback as well from SOX.
Yeah, but the typical in the flue gas is something that chemical industry considers a big issue. So
we have tested in real. We have tested real flue gas when we have both. So
that's great. Okay, thanks you a lot for the nice presentation. So let's proceed to the next talk. That will be given by Dr. Maria Teresa Izquierdo from the Spanish National Research Council. And she will talk about operational key issues in the development of flexible bio-CLC. And this work is part of the project BioFlex CLC.
Okay, thank you. Okay, so before starting talking about our participation in the BioFlex CLC project, I'm going to introduce about CSIC. I don't know if everybody of you knows about this institution. After I talk you about the concept of chemical looping combustion, that is the base of the project, and our experience on CLC. And after about the work package 2, the activities of the CSIC. And I will talk you about the first experimental campaign and the ongoing work. Well, the BioFlex CLC project is composed of 10 partners from 7 countries. One of these is the CSIC. The CSIC is the Spanish National Research Council. That is the largest research institution in Spain. It has about more than 120 institutes throughout the Spanish geography and covers all the fields of knowledge from basic research to technological research. About 1/3 of our budgets come from external funding. And one of the institutes from the CSIC is Instituto de Carboquímica in Zaragoza, just in between Madrid and Barcelona. This is the institute from CSIC, from where I come from. This is my research group. We are 9 permanent researchers with permanent positions, 7 PhD students, and 3 technicians. Well, our role in this project is mainly on the chemical looping and fluidized web combustion. And so, first thing, I'm going to introduce you to what is the chemical looping combustion. The idea lays on that commercial CO2 capture processes have important economical and energy cost due to the separation step from CO2. So to avoid this CO2 separation from flue gas, the reaction of combustion is split into reactors. One reactor is the fuel reactor, in which the fuel is introduced and is burned with an oxygen carrier. That means that it's not mixed with air. This oxygen carrier is reduce the oxidize the fuel, and we obtain CO2 and water vapor. After the condensation of the water vapor, we obtain the CO2 almost pure. This oxygen carrier that has been reduced because has given the part of the oxygen to the fuel is regenerated in the air reactor in contact with air. So we obtain a flue of depleted air, and the oxygen carrier is oxidized again for another cycle. So the oxygen carrier is continuously circulating between both reactors. And no, there is no mixing between the air and the gas in the fuel reactor in no moment. The key of this process is, of course, the oxygen carrier. The oxygen carrier is mainly based on the metal oxide that has to be high selectivity towards CO2 and water vapor, enough oxygen carrier, oxygen transport capacity, chemical and mechanical stability along the cycles, adequate particle size for fluidization. It has to be environmental friendly and low cost. Well, at first, this concept of chemical looping was developed for gas fuels. But when this process was extended to solid fuels, Two concepts arise from it. One was the in situ gasification chemical looping combustion, in which we need a fluidized agent that can be water or CO2 or a mixture of both. That with this we gasify the char to CO2 and hydrogen, and this is burned with the oxygen carrier. The other approach is the chemical looping with oxygen coupling. In this case, the oxygen carrier has the ability of release oxygen gas, and in this case, because there is oxygen gas in the fuel reactor, the combustion can proceed as a conventional combustion. So in our group, we have a lot of facilities to prepare the oxygen carriers, to characterize, and several continuous units for test these processes with gas fuels, liquid fuels, and solid fuels. The unit that is going to be used in the BioFlex CLC project is the unit that was built in 2013 with a nominal capacity of 50 kilowatts for CLO and 20 kilowatts for in situ gasification CLC. It consists of two reactors, the fuel reactor and the air reactor. There is also a carbon stripper. The carbon stripper was designed in order to recover the charged particles that can come from the fuel reactor, in order they don't reach the air reactor, in order to improve the combustion efficiency and when the CO2 capture efficiency. And also loop seals in order to avoid the mixture between the gases between the two reactors. We can also control the circulation of solids between the two reactors. This is important because with this we can maintain the temperatures between the air reactor and the fuel reactor. As you can see, this is a picture of the installation, and we have the reactor has a height of 4 meters. The air reactor is a height of 4 meters and 80 centimeters. Well, in the past, at the beginning, we start burning coal in this unit, but in the last years, we burned several biomasses, different wastes, and we have about near 100 hours of CSC experience with biomass and wastes. One of the main milestones for CLC is in 2023, we obtained negative emissions with first biomass fuel CLO in this continuous unit. Well, this morning, I think the coordinator of the project has given this picture about the objectives and the concepts of the BioFlex CLC project. The idea is to make flexible between circulating fluidized bed and the chemical looping combustion concept in order to obtain heat and power with zero emissions with circulating fluidized bed or negative emission with CLC operating conditions. Concerning we are involved in the work package 2, and this is in this timing with the CSIC activities for this work package. In the task 2.1, we made the selection of the biomasses according to the criteria defined in the project, the relevance for industries in Europe, the relevance for energy companies that are included in the consortium, the composition with respect to reactive phase species, and the availability at the scales and size needed for testing. So these were the biomasses selected: the pellets, pine wood pellets, olive stones, branches, and treetop chips, and refuse-derived fuel. In our institute, in the CSIC, we use 4 of these biomasses: the pine wood pellets, the olive stones, the branches, and treetop chips, and the RDF. And on mainly highlight the highest content of the RDF and the highest high content of the ashes of the olive stones. The task 2.4 was the adaptation of the 10 kilowatts. That is a unit that is at Technological University of Chalmers in Sweden, and our plan, the 20 kilowatts pilot with post-oxidation chamber and packings. This is the, as I've shown you before, this is the was the original layout of the installation, but we have to do some modifications for the technology. Remove the particle stripper because this unit, in order to separate charged particles, works well with very fine particles, but with pellets, our previous experience is that it don't work well. And we obtain a space to put a post-oxidation chamber that now is planned to install through the different modeling that is been carried out by other partner of the project. And also the compounds to be analyzed during the experimental campaigns will be the most important and in this list. The task 2.5 and 2.6, the investigation of the Bioflex CLC in the both retrofitted units, and also to investigate the fate of sulfur oxide and nitrogen oxide. And with the objective to conduct experiments in CLC mode and in a conventional circulating fluidized bed, with and without oxygen carrier, to analyze the behavior using packaging materials and to analyze the behavior of the post-oxidation chamber in the CLC operation mode. At CSIC, we have designed 3 experimental campaigns. The first, using conventional circulating fluidized bed combustion without oxygen carrier, using sand as a bed material. The second experimental campaign, conventional circulating fluidized bed combustion with oxygen carrier using ilmenite as bed material. And the chemical looping combustion mode using packing materials and a post-combustion oxidation chamber. Well, concerning this first experimental campaign, we use only 1 reactor. That's the idea, the flexibility to use or CLC or circulating fluidized bed. In this first campaign, we used only 1 of the reactor and the other was standby. We use, as I told previously, sand as material. That means there is not oxygen carrier in the bed. We use the reference conditions at 150 degrees C, an excess of air of 20%. But also we use other temperatures, excess of air, and supercell gas velocity with a variation of the secondary and primary air ratio. This first experimental campaign has been recently complete. And you can see here some profiles on a typical experiment, the profiles of temperature, profiles of CO2 evolution and oxygen evolution, the profiles of NO, and the carbon dioxide. In all the cases with the 4 biomasses and using the different experimental conditions, the thermal power reached was always near the 20 kilowatts. That's the nominal thermal capacity of the installation. And also the combustion efficiency was always higher than 80% in all cases. Here we have comparative emissions under reference operating condition with the 4 biomasses. It's relevant than only with the LDF we obtain SO2 evolution because the higher sulfur content of this waste and also higher nitrogen, NO, because of the higher nitrogen content of the wood chips and the LDF. And in the case of LDF, we also obtain ammonia emissions, probably that has a high nitrogen content. In all the cases, the tar evolution was low. We have some experimental problems, some operational issues with some of the biomasses used. In the case of oil stone, after about 10 hours of continuous operation, we experimented a defluidization. So we opened the boiler and we found some agglomeration, which was unexpected completely for us. And using scanning microscopy, we saw that the particles was sticky together. And studying more in deep what can happen, we saw that the potassium was was in the surface of the particle, not distributed on the particles. And I told you before, this oil stone has 30% of potassium in the ashes, so this can be the reason of this behavior. In the case of refuse-derived well, in this case, we suspect that the emissions of SO2 should be higher than we obtain, and we analyze what will happen with sulfur. And we can see that in this case, calcium was migrated to the surface, and probably this calcium are the responsible to capture some sulfur, and so the emissions with the flue gas were lower than expected. So despite the first experimental campaign was completed, we are now discussing and analyzing the results we obtained. But we have just started the second experimental campaign with using ilmenite as a bed material in conventional circulating fluidized bed. We have started with the pine wood pellets. And regarding the third experimental campaign, we are commissioning the building of the post-oxidation chamber according with the design parameters given by other of the partners of the project. And also we have we now have the packets at ICB and at CSAC because we have purchased them a few weeks ago. So that's all from my side. If you have some questions.
Yeah, thank you very much. Have time for question. From my side, the question has to do with the interesting stuff that you showed with potassium and the calcium. So what did you observe? You saw that the combustion rate was start decreasing with time. This is what you observed, some kind of a degree or no?
No, the problem is worse. The problem is that we need a defined particle size to that there is fluidization at the conditions we use. Usually the particle size of the bed material is about 100 and 500 microns. The problem is the particles are sticky and make agglomerates, and these agglomerates lead to the defluidization of the of the system. There is no fluidization. If there is no fluidization, there is no mixing, there is no working properly.
Okay, so the main issue was that.
Yes, it's an operational issue more than the activation. That means.
Yeah. Did you observe some kind of increase in the performance, let's say, at the beginning of this process of when the potassium and the calcium, they start segregating, sometimes they can act as enhancers or boosters for the reaction before they start becoming?
No, for us, well, there is other partner that is specialized in the interactions between the oxygen carrier and the elements of the ashes. In this case, it's not it's not an oxygen carrier. It's only a bed material that we used before in order to compare after with the performance with the oxygen carrier working in the same conditions. But it's an important issue, always the interaction between the ashes and the oxygen carrier, because they can give problems, operational problems like this. Usually, at first, the particles of the sun are silica, and they're well distributed. The problem is when you introduce a fuel with ashes, and these ashes interact with the bed material, and they are on the surface of the particles, and this can be sticky with other if they are put in that.
Yeah, clear. Thanks a lot. Other question? If not, let's take the speaker again. And there is one. Sorry.
Thank you for your presentation. So I saw that you combined oxygen with the fuel, and I wanted to ask where your source of oxygen is from. Is it from an air separation unit? And if it is, I know that is quite expensive. So do you have any comments about?
We don't use oxygen. We use an oxygen carrier. Not is the case now with sun. When we use ilmenite, for example, is the next experimental campaign. The ilmenite gives the oxygen necessary for the oxidation. So there is no air. That's the tricky of the chemical looping combustion. There is no dilution with the air. You introduce the fuel, introduce agent, CO2, water, or mixture of both, and the oxygen carrier. The oxygen carrier gives the oxygen necessary for the reaction. When this oxygen carrier is spent, goes to the air reactor, is reoxidized again. In this reactor, you introduce air, but never there is a mixing between the air of one reactor and the gases of the other reactor. That's the reason we obtain almost pure CO2 flue gas mixed with water that can be easily separated. So we say that the CO2 capture in this process is inherent to the process. There is no separation.
I have to move on. So thank you very much for the presentation. Let's take a figure. And we're going to move in the last presentation for the session and for today, which will be given by Dr. Davide Scarpa from University of Antwerp. And it will be about unlocking green urea. And we're going to see how to investigate reactor parameters for electrochemical synthesis from CO2 and nitrates. And the work is part of the project CONFET. So, the floor is yours.
Okay. Good afternoon, everybody. My name is Davide Scarpa. I am a postdoctoral research at the University of Antwerp, Belgium, and I am working within the framework of the CONFET project, whose main objective is the production of a lab-scale prototype for the production of green fertilizers. And in particular, my focus is on the production of green urea and the investigation of lab-scale parameters for the electrochemical synthesis of green urea, starting from carbon dioxide and nitrates. But before delving more precisely into the details of what I'm doing, I always like to do an overview, to give you an overview of the process. So I will be starting by telling you we humans produce over 180 million tons of this molecule, urea, per year. 90% of them are adopted in the agricultural industry as fertilizer. Why using urea as fertilizer? Well, because among all the nitrogen-based fertilizers, it has the highest amount of nitrogen in its molecule. And nitrogen is fundamental for the growth of the plant since it's a key component in chlorophyll. So it's fundamental for photosynthesis. And no wonder that urea, which is also quite a stable, non-hygroscopic solid, is also easy to store and to handle. And it's quite inexpensive the way it is produced right now, which is through industrially through the Haber-Bosch Bosch method process. It's almost 50%, so accounts for almost 50% of the whole nitrogen-based fertilizer market. A market which is increasingly in the spotlight since it's causing over 5% of the worldwide greenhouse gas emissions, and it uses 2% of the whole fossil-based energy. So we need to solve this problem since right now urea is fundamental for agriculture, but the way it is produced right now, it's not sustainable at all. At the same time, I'm not going to spend time about this molecule. We are trying to take away from the atmosphere, and which has been increasingly increased, no pun intended, over the last years. Another important pollutant we would like to get rid of is the nitrate. Nitrate is one of the most widespread pollutants in groundwater and also in drinking water. It comes from agricultural runoff water, so from the abundant usage of fertilizers. And as you can see from this map, its presence in drinking water has been increasingly over the last few years, so that the WHO set a threshold limits of 50 ppm, which has been exceeded in many parts of Europe. You can see the push pins red and orange, which shows that these thresholds have been exceeded. And all over the world. So the idea is to try to combine these two pollutants electrochemically to obtain urea in a more sustainable way. However, I took this picture from a recent review, which shows that so far the electrochemical reduction of urea remains at an early stage of development, characterized by a low TRL when compared with traditional processes. And so we can say that primarily so far, the research focus stays on fundamentals, that is on catalyst development and some tests made in batch age cells, while few are the attempts trying to scale up the process and try to optimize it. And one of the attempts is mine, indeed. My objective is to achieve an optimized lab-scale urea electrosynthesis, and I'm going to do this in two different ways. Trying to tackle two different aspects. So I'm trying to optimize the parameters of a lab scale flow cell, and at the same time try to optimize the parameters of the electrodes to be integrated into the flow cell, which, and I'll be coming there in a minute, are gas diffusion electrodes. But talking about the Confetti project in which I work, you've seen this scheme in other presentations, and I'm not going to spend time about that. I'm located here, so I'm trying to find a way to produce it lab scale electrochemically. And more precisely, I'm work package 3, which is structured in 3 tasks. 2 of them almost finished, while the last one, which has to do with optimization, just started a few months ago. So it will be due by the middle of next year. Coming to the first task 3.1, which has to do with the electrodes productions for different electrolyte systems, including mine. My very first objective was to try to fabricate proper electrodes to be integrated into the flow cell. And the choice fell, of course, on gas diffusion selectors, which are fundamental when aiming at current densities of industrial relevance and aim to address the mass transfer limitations problems, which is typical of other systems, like, for example, H cells, flash cells, by directly address the CO2 to the catalyst layer so that it will react with the nitrate in the solution in the so-called channel phase boundary to obtain the targeted product, that is urea. And more precisely, I wanted to study the effect of different degrees of hydrophobicity of the gas diffusion selectors. That's why I selected a set of 5 different types of GDL, so the base of the GDE. And in particular, I selected them with different PTFE content, so with different wet proofing, ranging from 0 to 30% weight. And then I deposit onto them, which is so far the most active and selective catalyst towards urea electroproduction in literature, which is silver. And I deposited either in form of thin film or silver nanoparticles, by also changing the loading, ranging from 0.5 up to 1.5 milligrams square centimeters. Right now, I am there, so I'm trying to focusing on these GDLs. So I prepared overall several batches of 5 GDLs each. What are the deposition technique that I adopted? Briefly, there are 2. One of them is pretty straightforward, and it's the airbrushing with spray coating or of an ink made of commercial silver nanoparticles and an ionomer. This main aim is to work as a binder towards the nanoparticles. And it's pretty easy to preparation, so you just make the ink, sonicate it for a certain time, and then spray coat it with a pistol for a certain time and at a certain temperature. These are the results for some GDE. And at the same time, since I also wanted to get rid of the effect of the ionomer into the formulation, I also sputtered GDE, so a thin film of silver, by using this machine, the plasma sputter coating, which uses plasma, which bombards a metal target, in this case silver, which then ejects the atoms, which will coat the surface of the GDL. And that's the result of some of the GDE you can see. Before starting with the electrochemical tests, I also wanted to test them, and I used optical contact angle measurements under ambient conditions by using cell drop goniometry technique. You can see here the results of the average contact angle, which are in line with what I would expect. Well, the GD, as for the GDL, so the black dots, the black curve, as the PTFE content increasing, we see a slight increase of the contact angle. For the sputtered silver GDE, it's possible to see a quite understandable trend, since as the silver loading increases, since silver is hydrophilic, there is a decrease of the contact angle, an average contact angle. As for the straight ones, there is not such an evident trend in decreasing of the contact angle, and that has to probably do with the presence of the ionomer in the formulation. So coming back to the other task which I carried out in parallel, I also dealt with the fabrication of a lab scale flow cell, which you can see here in this picture, with all the components. It is based on a commercial design, which has been, I would say, extensively modified. One of the modifications that I made, which stands out most, is the presence of this flow plate of this separate window, from which it is possible to appreciate the back of the GDE, and so be able to pre-optimize the conditions before starting the test, so that I can avoid problems, such as, for example, the leakage of the catalyte through the GDE of the gas chamber. More precisely, it is a 10 square centimeters active area flow cell, which has 3 chambers. So one for the catalyte, the other for the anolyte, and then the gas side chamber, which interacts with the catalyte chamber through the GDE, which is housed in a titanium current collector. While on the other side, the oxygen evolution reaction runs smoothly and stable, thanks to the presence of the iridium-based anode. As for anolyte, I use nitric acid, which in combination with the nathion, the 17 proton exchange member, supplies the proton to the other side. And as for the catalyte, I'm using potassium nitrate and potassium bicarbonate. I also needed to set up the setup, and so it is made of basically the reservoirs for the catalyte and the analyte, which are in recirculations. What stands out here is the presence at the gas outlet of a needle valve, which I wanted to use to be able to go in flow by. At the moment, it's closed. So I'm going flow through, I'm pushing all the CO2 through the GDE. That is because this requires me less pre-optimization. So it's fundamental for the first screenings. So after setting everything up, I started to do some screenings to be able to see whether I was able to assess urea or not. I picked up one of the first screenings that I made here, which I compare under the exact same conditions, both the sprayed and sputtered versions of 1-GDL, so the TCP 5%, so at PTFE content of 5% weight. And I'm also comparing the sprayed and sputtered versions on a commercial Sigracetonin IBB GDL. And from you can see from here that the sputtered GDE BA is much better in terms both of parallel efficiency of urea and urea production. And that is in line with what I would expect from the literature, in which the sputtered GDE, silver sputtered, BA is better. It's considered to be the benchmark catalyst. But I wanted to go further. I wanted to understand what was going on in the system. So the next step after picking up sub-optimized GDE was to test it under different current densities and try to detect both the liquid and gaseous products. So as you can see here, as the current density increases from 10 to 50 milliamps per square centimeters, the Faraday efficiency urea decreases from 11 to 4%, and the system tends to evolve towards CO and above all towards ammonia. To be able to see whether this was be due to the GDE, I also changed the GDE, in particular the GDL. So I did a test on the same under the same exact conditions. I just add current densities just to be able to understand what was going on the sputtered TCP 20%, so with a higher PDFP loading. And although I get higher urea per light efficiency and lower current densities, the trend is more or less the same. So I see a lot of ammonia. So the system is going towards ammonia production, which is the side reactions of this process. And at the same time, I'm also seeing a lot of nitrites into the system. So this made me understand so far that the way to proceed is to optimize better the systems. And for example, try to use less nitrates as source. So to decrease the concentration of the catalyte. And that's what I did as a last test. So far, I decreased the concentrations of the potassium nitrates, the source of nitrates, from 0.1 molar to 0.05 molar. And I detect an increase of the parallel efficiency of urea from 17 to 32, as well as an increase of the urea mass production rate, which made me overshoot 2 of the KPI of the project, which is, I would say, quite a good result for starting. So to conclude, I was able to assess that by performing a complete screening of both liquid and gaseous products, that could be the route follow to be able to track trends and then to identify how to optimize the system. So far, I realized that the Agri-Sputtered TCP 20% behaves a bit better than the Agri-Sputtered TCP 5%, and that's to do with the PDF content, which is changing probably a lot of conditions in a way that they favor more urea. I managed to exceed to the KPI of the systems, the project, on one of them. So for the future, my main is to complete the series to be able to understand what happens by changing the concentration of the electrolyte also at higher current densities, which is much more important in terms of industrial relevance. I want to further study the relationship between different GDEs and the performance towards urea electroproduction. And finally, I'm trying to optimize better the system in order to achieve the other KPIs and going beyond to get a good production of urea as well as selectivity, and above all selectivity, I would say. Thank you very much for attending the session.
Thank you, David, for an interesting presentation. Questions? It's the last presentation, so we'll have.
Thank you for your presentation. I have a question. Did you perform atomically labeled experiments to determine the origin of the product?
You mean for the detection for which?
The detection, for example, you're obtaining ammonia.
Yes.
Where is this ammonia coming from? Do you know if it's nitrate?
Well, an idea would be, for example, right now I am testing ammonia through UVBs. So I'm using a colorimetric method to understand the difference.
What I'm asking is to use, for example, nitrogen 15 instead of nitrogen.
We haven't done it yet. That's something that we could do.
Because especially for ammonia, this is crucial to know the origin of ammonia.
But according to literature, seems that this a possible byproduct is ammonia. So,
but in science, you need to prove
to be able to express that better. Yeah.
I think that's mainly when we have the nitrogen, but in NOx, it's typical byproduct. The problem is when you have the nitrogen, you need to understand the source of NOx. If there is NOx in your system, because this will give the ammonia, in this case, you're feeding the NOx, I suppose. However, I was wondering, because always triggers me when I see that you want to compete with Haber-Bosch with an electrochemical route. We're talking about 10 milliamperes. So what are the targets for commercialization, or at least to have something that could be commercialized?
Yeah, the targets are to reach a higher current densities for sure. But at least since I explained before that we are low tier L, so we are just the beginning of this area of work. Reaching Faraday efficiency for this system, which is one of the few systems that we started in a lab scale environment, over 20%, which the result you see, you saw it. I think it's a pretty good result for the moment. So,
but of course, you need to sustain that at the very high current density, because otherwise you cannot compete.
We also have to test the durability of the system as well, which is something another key point, which has to do for the future.
Good luck.
Thanks.
Other question? If not, let's thank the speaker. And with this now, we finish the session. So see you everybody in the social event and dinner that will be at 5:30. And yeah, thank you for joining.